In the cities of tomorrow, autonomous cars will allow for completely new opportunities to optimise mobility while offering luxury transport for users. At present, cars are controlled by traffic lights, which disrupt vehicle flow and increase emissions and journey times by requiring more frequent stopping and starting. And pedestrians don't really fit into this picture because crossings are dangerous and poorly optimised. Autonomous vehicles bring an opportunity to reshape how vehicles and pedestrians interact on our roads. We have, therefore, been considering how we might design for better integration and communication between autonomous and non-autonomous road users in our cities. This is where our solution comes in. We redefine the way cars interact with pedestrians and each other at junctions. Traffic lights will be removed, and instead of treating intersections as junctions, they work like roundabouts. Every car gives way to the right and can move onto the junction whenever it is safe to. In addition to this, pedestrian crossings are moved away from the main intersection to make sure they don't interfere. In order to maintain road safety in this less structured environment, we've developed new methods for vehicle-to-vehicle and vehicle-to-pedestrian communication. Vehicle-to-vehicle communication, powered by VHF radio networks with a range of around 250 metres, will see each car broadcast information about its movements to a local network. Its current position, speed, and what it intends to do next will be shared. Any cars within range will pick up this information and use it to coordinate movements around the junction. In this example, a car approaches from the left, preparing to turn right, and at the same time, another car approaches from the bottom, intending to go straight ahead. If both of these cars were to carry on, they would crash, so the traffic control system steps in to slow one of the cars to avoid collision without having to bring either car to a complete stop. The car on the left's manoeuvre is more complicated and will take more time, so in this scenario it's more efficient for it to slow down. The bottom car would have to slow down more to let the left car pass. T-junctions will necessarily work slightly differently, because main roads are often joined by a side road and we don't want to disrupt the flow of traffic on the main road unnecessarily. Because of this, T-junctions will often require cars in the joining flow to stop, but for less time than in the current system. Priority is given to cars on the main road, and the TCS looks for gaps in the flow of cars into which it can fit the cars waiting to join. In this example, the system will detect this gap and begin to slow these cars down so that it can bring the waiting car out into the main flow. We've also added electromagnetic vehicle sensors to the roads before each junction so that they can still react to non-driverless vehicles which aren't communicating with the rest of the system. The drivers are told what to do by these dot matrix displays positioned before each junction. Vehicle-to-pedestrian communication will occur through the crossings themselves. A pedestrian intending to cross the road stands on a piezoelectric detection area. The data from each vehicle is processed, allowing the crossing to communicate when the pedestrian can safely cross the road through a lighting system. The bar on the vehicle and lights on the ground are red when it's unsafe for the user to cross, and change to green when there is a safe gap for crossing. In the event that a user has been waiting for more than 45 seconds, the TCS will work to create a gap in the traffic for safe crossing through controlling speed, thus eliminating the need for cars to stop completely. In future cities in which autonomous vehicles are a staple, junctions and pedestrian crossings can be redesigned to ensure mobility in future cities is safer and more efficient.